Hello, my name is Yoann. I'm a third-year PhD student at the University of Cambridge, where I'm working with Paul Schiller, Lengeras, and Most on stochastic inflation and general relativity. We are interested in vacuum, quantum diffusion, and non-perturbativity for the inflaton using numerical relativity. So let me tell you about it. So this research is obviously about inhomogeneous inflation. So very briefly, inflation is studying a scalar field. In most standard models, it's a scalar field going down that kind of potential, so a flat portion that provokes a sort of cosmological constant behavior, a very fast exponential expansion of the universe, and it's metric. And then the field goes down the potential and decays into more modern particles. The equations are pretty simple. Fine, you probably have seen them, and they have obviously a back reaction at stake. So here the Freeman equations would link, the drift for the field would be driven by the expansion, and vice versa, the expansion would be sort of sourced by the spacetime's content, i.e. the field. Right, and it becomes more complicated when you add quantum perturbations, which we believe are the source of any inhomogeneities today. And so we want to be able to describe what happens to perturbations when they evolve through GR, through the potential, until the end of inflation. Now, the simplest cases like that one are only required in some scales and only within a given precision. Okay, we still need to be able to describe everything because there's just so much regimes that we haven't constrained yet, and we need to be ready for that. For instance, how do I make a prediction for that kind of potential? It seems pretty difficult analytically, and this is a very common model if you look at UV completion theories and you try to get the potential for that. You can have other potentials like this one with an inflection point where the field almost stops, and again, it's pretty difficult to derive things analytically, although some people manage. So what if there's no tractable unequal solutions? What if the couplings blow up? What if you leave perturbation theory and where QFT is not valid anymore? So we are in desperate need of solutions, and I want to convince you that there are some numerical solutions. Numerical solutions thanks to the nature of inflation. Now, for the end of the intro, there is a lot about being able to make predictions, as I said, and that's what this research is about. If you look at their most recent Simons observatory forecast for the power spectrum, for instance, we know that it's going to be an improvement by 1 order of magnitude for the small scales. And similarly for bispectrum shapes, it's going to be better constraints on more scales too. You can also look at other experiments. We will have more data, for instance, for like constraining pyramidal gravitational waves. And that means that we really need to be ready, okay? New experiments will probe with higher precision and more linear scales and even like those gravitons. So there's desperate need for precision prediction on all scales and all regimes and full general relativity. Now there is already a lot of solutions out there and we can learn from them. So let's have a look at the numerical landscape. One could implement the calculations of QFT on spacetimes. For instance, you have a lot of integrals to perform there. You could just perform them numerically. But the easiest thing to do is probably to differentiate these things to get what we call the transfer equations for the correlation functions. Right, it's just a system of differential equations for the correlation functions, and you can solve them like any other differential system. There has been a very recent implementation with a lot of extensions to previous ones. The most recent implementation is CosmoFlow by Worth and others. Here you can see one of their results for the 3-point function of the inflaton in Fourier space due to not the self-interaction, but due to, or gravity interaction, but due to the massive scalar interaction. Okay, so it's a very interesting software. Great features. It includes most of quantum effects. It is consistent with general relativity, and it is giving you a lot of freedom in the modeling. It is very fast to run. You can just run it on a laptop, and it includes gravitons, so nice for the study of pyramidal gravitational waves. Now it's missing some quantum effects. I believe that the software doesn't include quantum loops, probably because you could not close the system of differential equations, or you would have to make more approximations, I guess. And also, I guess, because there is no generic treatment of loops on curved spacetime, unfortunately. It's also a perturbative framework, so nothing about non-perturbativity. And when you work for each system, you need to declare which order and the interactions you're working at in terms of the coupling, at least. So that means non-linearity is only partial. Now, I want to convince you that promising numerics use semi-classicality. Okay, since we don't have quantum gravity, or at least we don't have one that can be easily implemented or so, but at least not one that we have tested properly and that we don't trust as much, we should use the fact that inflation is actually very convenient on certain scales. We should study inflation on those regimes. And those regimes are believed to be achieved by most models and for all scales at one point in their history. So this regime is the regime of classicality, and among others, Turbinsky pointed it out. He explained that, at least I can explain to you, that the Hubble radius is a scale that shrinks in comoving space during inflation. And when the wavelength of a given perturbation becomes bigger than this, then this mode becomes mostly classical. Okay, depends on the definition of classicality, actually, but it becomes mostly classical. And so that means you can study this higher system. Okay, and so it's up to you. But if you're interested in quantum corrections, you should study the previous methods. If you can place yourself in those classical regimes, usually called late times, then use the semi-classical techniques because they allow you to study nonlinearities fully and non-perturbativities. So that's what we're going to focus on in the following. You can also have a look at our articles that compares the two in the perturbative regime for the bispectrum. Now let's have a look at lattice cosmology, which is a semi-classical approach in the sense that it evolves the classical equations of motion from the quantum Gaussian noise. Okay. So that means you place yourself on the lattice, you evolve the equation for the scalar field, including its gradients and the expansion on which it evolves, and you include some sort of back reaction, a heuristic back reaction via the average Feynman equation, which is feeding h, and h is fed by the value of phi, etc., etc. Okay. So you can get nice PDFs with tails that could, for instance, enhance the production of primordial black holes, such as in this case with the ultra-slow rule. It's also a great framework. It is non-perturbative, fully nonlinear. It is a simple theory. It is, I believe, faster to run than general relativity because you don't have to run the whole space-time. But it is certainly missing, well, quantum subbable scales, but we said we were not interested in those anymore. It misses geometry effects, gravitons, but also some sort of coarse-graining. By that, I mean that in this case, we are giving all the perturbations that we can put in the box at once at the start, okay? As in all the modes, the Fourier modes. But actually, if you look at stochastic inflation, it seems more natural to give to the simulation each mode that has just become classical at this given time step, so that all modes have the same time, have the same amount of time in the UV and in the IR, and are treated equally, closer to an EFT framework then. So when you do that, you get Starobinsky's Langevin equation for the scalar field, and recently it's been extended by collaborators who basically managed to make it more consistent with general relativity, essentially. So each time step you have noise that makes the different modes that have just become classical enter the system. And this has been implemented. You can see it with this article by Mitsukuchi and the software called Stolas. It's really nice, very powerful too. Non-perturbative, it has the coarse-graining, and this whole method has a lot of established primordial black hole prediction pipelines, and it includes also the geometry, as I said, with recent extensions. What's missing, though, is a simple link to observations. The formalism is pretty heavy and pretty case dependent. It's also missing gradients as opposed to lattice cosmology. So it cannot study phase transitions or near Hubble scales phenomena, but also gravitons are not included. And finally, some other complementary technique is numerical relativity, where you essentially evolve your whole space-time. But that means you need to have found initial conditions that satisfy the highly nonlinear constraint equations of GR. Some of our collaborators have managed to find a way to do that, okay, and studied the robustness of the robustness of inflation against inhomogeneities. Okay, so sometimes inflation could fail because the inhomogeneities are too strong and stop inflation from happening. Some other people, because GR allows you to study those strong regimes, have studied pre-inflation where gradient and kinetic regimes can be studied, again using some numerical solver for the initial conditions. And also some preheating studying have been done. But the conclusion is that there's not been enough stuff done for inflation. And the reason is, so great on the features that are like non-perturbativity for nonlinear GR, the fact that it's a highly parallelized framework. The thing that's missing really is giving physical initial conditions that are closer to quantum fluctuations, and we also need more applications to inflation. So yeah, let's see if we can get all of these things that are missing in each of those bits together in one framework. Is that possible? Well, let's see. Okay, now I need to convince you that we managed to achieve that. Okay, so let's see how we can run full GR semi-classical inflation. So the first thing to do to include those physical perturbations in GR is finding a way to translate our cosmologist knowledge to numerical relativity knowledge. Okay, so here this is sort of representation of how we evolve things in GR. What we're going to need to do is feed our cosmology into the initial slice of this thing and then run it. Okay, so how do we feed this initial stochastic initial conditions like lattice cosmology would do? Well, first we need to find the spectrum of the perturbations. This is given by the Mukhanov-Sasaki equation, okay, which with this quantity R that sort of summarizes all scalar perturbations in one quantity that is gauged invariant at linear order and gathers spatial metric and field perturbations. The details don't matter. And this is where you put your quantum initial conditions, okay? So we found a way to solve the sort of historical problem of how to input rigorously those perturbations in a sort of unique and well-defined rigorous way. So to do that, you work at linear order. It's pretty much enough to satisfy the constraints at linear order. So when you do that, you can find the expression of those. So essentially, you start with a background homogeneous, so that's easy to find that to solve the constraints, and then you add some small perturbations that are all functions of this R. Okay, and so when you do that, you can just plug that in your simulation and start running it. Okay. So we are doing the same as lattice cosmology, except that we have the geometry now. So we can tick the box of theoretical accountability, full geometry engage, and no long wavelength approximation. So let's see what it gives on GRTrumbo, which is the software we've used for a vanilla, very linear quadratic inflation. So what you can see here is the comparison between, so for the field, the momentum, and K, which is essentially the local H. You can see the background. Okay, so the blue dots are the actual GR simulation from which you take the average, and the red is the Friedman evolution. You can see they agree perfectly well, and you can keep going on the spectrum. If you look at the spectrum, you find that the linear prediction is actually pretty close to the box once you extract it. Obviously, there is some sample variance, but they're really close, so that's a good confirmation that we're doing the right thing. And this is the spectrum of perturbations that is showing it right. Importantly, the constraints are perfectly satisfied too. Here the dashed dot line is, so these are the Hamiltonian and momentum constraints. The dashed dot line says where you should not be. Okay, if you're there, that means that you're violating the constraints at the same order as, with the same magnitude as your perturbations. Okay, obviously we want the perturbations to cancel perfectly in terms of energy balance. Okay, that's what the constraints are for. So that's good. You check that. Numerical accountability is good. Now, just to show you how it looks like with respect to this, change in the slope of the spectrum, essentially it means that after a few e-folds, we're going to observe the small scales starting to be privileged. Okay, so that's what the tilt in the spectrum shows. Okay, so that's good, and it's something we are familiar with. So now we've verified this, and you can also do that actually for gravitons. You can see the work of my colleague Erica Florio. So let's see for non-vanilla frameworks, okay, scenarios. Ultra-slow, for instance. So here we start with a slow roll period, and then we slow down. The field almost stops on the inflection point and creates something non-perturbative, hopefully. So the background is pretty much the same, okay, no change with the homogeneous case. And then when you look at the contrast, you can see that the field's contrast is going to shrink. It's going to shrink greatly, whereas the curvature perturbation, which is I guess here mostly the spatial metric, is going to increase drastically here up to 0.3. Okay, so we are out of perturbation theory, and this behavior is actually in agreement with the previous paper on this type of potential. We've also extracted some cumulants to look at non-Gaussianity. It looks like some is produced, but we are keeping that for future work because we need to do a proper statistical analysis. Anyway, we can tick the box of non-perturbativity. Now, some results from a non-vanilla, very exotic regime, the axion monodromy case, where here essentially you add some resonance to the quadratic model and run it. Okay, so this is chosen big enough, and what you see is that there's going to be a resonance between the sort of frequency of those bumps and the quantum frequency of your modes. And what you can see is that the background and the average don't agree anymore. And that's because you now have two types of regions that have managed to get over the bumps and continue for successful inflation, as you can see on these two. So essentially the representation of the overdensities, and here the PDFs. Okay, but some of these perturbations have stayed stuck in the wells. You can see it here. Okay. And this is also in qualitative agreement with the work by a lattice cosmologist. In particular, the spectrum is also something we qualitatively at least agree on, because we don't have the same initial conditions. Anyway, so this is fully nonlinear approach, and it's good. Now we can also incorporate stochastic noise, and let's do that. So to do that, again, we want to not include all the modes that we can in the box initially. We want to feed them at each time step. So to do that, we need to work with a window function, and believe me, we managed to do that. This is the result we found in our first paper, where essentially we were trying to coarse-grain general relativity. So I've talked about it in diverse talks, and I'm just going to summarize it here. You can have a look at the paper if you're interested, but essentially we managed to find a way to have those modes enter at each time step and still satisfy the constraints, okay, which is a first, which means we are physical, and that's good. The energy balance is right. And then you have the amplitude of those Gaussian stochastic noise given here. And they're pretty simple. They come from the coarse-graining of the Mikhailov-Sasaki equation, actually, behind the scene. It's pretty simple, but it's a difficult, obviously, system of equations. And note that this can also be done to account for gravitonic UV perturbations becoming classical. Okay, see our article. So that means we can tackle primordial gravitational waves in the future. That's great. Good points too. It's gauge invariant, and it's valid beyond the long wavelength approximation, as opposed to stochastic inflation. So the good news is that we managed to implement that. That takes a lot of time to do GR. So it's basically stochastic partial differential equation. It's pretty difficult to implement. We've managed to get tests running on the constraints, so it's working, and the spectral agreement is clear compared to the other case. And we need to run more cross checks to verify that everything is right, but we are about to enter a really cool era of simulations, so we just need to run more examples. But now the coarse-graining has been achieved, and so it's great news. So left to do is running many applications. We need to take that box for the prediction power by running more examples, extracting new signals, for instance gravitonic or scalar bispectrum shapes, extending that to multi-fields, AFTs, etc. And of course, it's a method with its own caveats, right? Some methods are better than others for certain things, but that's good, okay? And that's how we do science.